Yeah, our next speaker actually is from Xilinx, who is becoming a very big name in AI. Is anybody here interested in AI? Let's have a show of hands. I count 1, 2, no. That promises to be a really big part of the overall field. And so we've got here Manish Muthal, who's VP of Data Center for Xilinx. He's been working in their hyperscale and HPC and enterprise customers for quite some time. He has come over to Xilinx from Broadcom, where he worked with multi-core processors, and before that was in strategic planning and architecture at Seagate and LSI. So let's have a round of applause for Manish Muthal.
Thank you. Good afternoon, everyone. Welcome to the post-lunch keynote session. I hope you're enjoying this exciting show as much as I am. We are indeed living in an exciting time where we are seeing massive shifts in both technology and business models, and that all has to do with the explosive and unprecedented growth of data that's happening right in front of us. I'm here today to talk about how data center infrastructure needs to evolve in the face of this massive data growth, and how we're going to apply the notion of adaptable storage acceleration platform to be able to tackle with some of the challenges with this data growth. I'm going to start out with a few key industry trends that are driving fundamental changes in the way we architect data centers. This one should be familiar to many of you. This one captures the evolution of microprocessor architecture and some of the brick walls that we have run into over the years. The first one that we ran into was when we saw the end of Dennard scaling, when we saw that we were not able to improve performance with every technology node as we used to in the past at the transistor level or improve power. In the early 2000s, we ran into the brick wall of frequency starting to flattening out for server CPUs. Very soon thereafter, while we innovated from a microarchitecture standpoint to deliver higher performance at the same frequency, we started running into the next brick wall around single thread performance. And when we did that in response, our industry innovated once again, and we ran into basically the multi-core architectures and started delivering higher performance through the adoption of multi-core architectures. However, we ran into yet another brick wall, and this time around it was the power brick wall. We can only pack so many cores in a given socket, given that we can only dissipate so much power from a given socket. So we have hit performance walls, we have hit power walls, and while Moore's law continues while slowing down, and we can continue to pack more transistors with every technology node on a per millimeter square basis, the reality is that the cost on a per millimeter square is increasing with every technology node. So we are also running into a cost power wall. So what is now inevitable is we now need to move to a paradigm of heterogeneous computing architectures. We are already seeing that happen across applications like machine learning training. We are already seeing that happen across newer applications around both machine learning, but also traditional applications like databases, video. We are seeing the adoption of FPGAs. We are seeing the adoption of GPUs. We are seeing the emergence of custom silicon to go complement CPUs in a heterogeneous architecture paradigm. Going forward, these accelerators are going to play a key role to help us scale performance in a cost and power efficient manner. So that's, I think, a relatively obvious trend that we all are aware of. What may not be as obvious is this second trend, and this has to do with the diversity and the evolving nature of many applications that need to be accelerated in our data centers. The chart here shows a plot of multiple applications and the amount of compute cycles as a percentage of the total compute cycles in a large data center. This study was done by Google, along with Harvard and Yahoo Labs and others. And what this points to is in a large data center, in a hyperscale class data center, the largest binary in this study, or the largest workload, consumed only 9.9% of the total compute cycles within that data center. And if you see the trajectory of this plot, you will see that even the top 50 binaries could only add up to about 60% of the total compute cycles. There's another chart from the same study that shows that there's a secular decline with respect to that 60% number. What that means is that the top binaries, even the top 50 binaries, are now accounting for less and less percentage of the total data center compute cycles. So effectively, what that means is there is no such thing as a killer workload or 5 killer workloads within large hyperscale data centers. So as we grapple with the diversity of these applications and also the evolving nature of some applications like AI, so we are definitely at the dawn of AI. We are seeing AI intersecting across pretty much all traditional industries, across multiple workloads within those industries. And as AI as a method intersects these different workloads, we are seeing that these workloads, the evolution of that workload is going to be faster than what can be met by custom silicon turnaround times. So basically what this points to is that not only do we need acceleration inside our large data centers, but we need that acceleration to be adaptable. If you look at a large hyperscale data center, not only are they dealing with diverse and evolving applications, but they're also grappling with the dynamic mix of these workloads. And this mix changes literally within minutes to hours within these large data centers. So large data centers now need to evolve to an architecture of adopting adaptable acceleration. FPGAs is a great device that can provide adaptability of acceleration, that can take on multiple personalities, that can become domain specific to go accelerate a variety of accelerators, a variety of applications, and do so in a dynamic manner. So think about FPGAs getting deployed at data center level, being attached to the fabric of the data center so that you can now orchestrate and control pools of FPGAs that can go accelerate certain applications like search, applications like machine learning, applications like video and database on a completely dynamic basis. This is where we are headed with respect to adaptable acceleration. So far, the two trends I talked about have to do more with compute and how accelerators and adaptable acceleration are going to be critical to go scale compute and meet demands. The next trend is an obvious trend that we all are aware of around the tsunami of data that we are all facing. And the reason why this trend is important is because this now has implications on the location of where adaptable acceleration needs to be deployed inside these data centers to be able to scale performance in a power-efficient and cost-efficient manner. What is important to realize here is that a lot of this data growth is coming from unstructured data. Fortunately, as we deal with the volume of data growing on us, our industry has been investing in flash technology, and we have been able to increase both the density and the performance as we move from 2D to 3D, from SLC to MLC to TLC to QLC. We have improved performance, we have reduced cost, we have increased density with flash, such that we can now pack more capacity inside each server, and we can pack more capacity inside storage, external storage arrays. However, what we need to now recognize is that we are now just about getting ready to hit into a new brick wall. And that new brick wall has to do with the amount of data that now needs to move back and forth between the storage subsystem, whether it's inside the server or whether it's external storage array, going back and forth to the compute, which is the server CPU. So I would like to now illustrate this specific problem, this specific brick wall that we're running into, and then talk about a particular solution framework that can help us address this problem. This picture here shows an abstracted view of a server architecture. You can extend and extrapolate that to imagine an external storage platform as well. What it shows is a dual socket server connected over PCIe to a storage adapter, which then fans out to a bunch of SSDs. Now, when we deal with 1 to 10 terabytes per server, say 2 terabytes per SSD, 4 SSDs in a server, for any application that is not data intensive, for any use case that is not data intensive, we can imagine an accelerator like the ones shown here in the red card there. It's a Xilinx card, and some of you are familiar with the work that we have done with Amazon on FPGA as a service, where a Xilinx-based card is plugged into Amazon's cloud instances to offer compute acceleration. So the compute acceleration paradigm here is basically fine for both the non-data intensive and even the data intensive use cases, because there is not as much data that needs to go to the CPU, not as much data that needs to go to the accelerators that are close to the CPU. However, if you now see as data increases, as there is more dense storage inside our servers and inside storage arrays, we will now start seeing bottlenecks from the storage adapter to the CPU and from the CPU to these compute accelerators. The reason is that while non-data intensive applications will be fine, for data intensive applications now you're talking about having to move tens of terabytes of data from the SSDs or from your storage, whether it's local or whether it's external, into the storage adapters, and then from the storage adapters into the CPU and the accelerators. The amount of bandwidth that exists from the SSDs to the storage adapter is typically much higher than the amount of bandwidth that's available on PCI interfaces going to the CPU and the amount of bandwidth that's available from the CPU to the accelerators. In many cases where there is no RDMA support, you're also now bottlenecked by the system memory, which is where you need to go through to be able to go accelerate these data-intensive use cases. So we are already running into a problem as we look at packing tens of terabytes of storage and running into data-intensive use cases where the data movement back and forth is running into these bottlenecks. The other key problem is around power. When you move tens of terabytes of data from the storage to the compute, you are moving a lot of bytes, and as a result, you're consuming a lot more power. This problem is only going to get worse. So as you look at packing hundreds of terabytes inside a server or petabytes inside external storage arrays, this whole bottleneck around the storage adapter to the CPU, and while I've just shown the server architecture, you can imagine this being a storage array wherein the pipe that's shown between the storage adapter and CPU now needs to go over your network fabric, which is even more expensive to go manage. So those bottlenecks to the CPU and the bottlenecks from the CPU to accelerator are now going to come in the way of providing acceleration at the level that is needed for hundreds of terabytes of data. Once again, power-wise, if you have to go move hundreds of terabytes of data from storage to CPU, or worse, you have to move it from external storage arrays to your server rack through the network fabric, you're burning a ton of power, which basically means that now you run into this new brick wall where you will not be able to scale performance in a cost and power efficient manner. So with that, basically what that tells us is that this whole old paradigm of moving data to compute or moving bytes from storage to server CPU is not going to scale as we move into the era of exabyte-scale data centers. The approach that we really need to go invest in now is really moving compute to data. And let me talk to that on this slide. So basically what this implies is that there are many compute functions that are data intensive, and I've listed a few of them here. The simpler ones, which I call storage services, from compression to erasure codes to data deduplication to RAID, these ones are the simpler use cases for data-intensive computation that can be offloaded and that should be offloaded closer to storage going forward. However, there are other computational functions like front-ending these NVMe drives and doing the front-end virtualization, moving on to database offloads, from key value offloads to query offloads to ETL offloads to media services like video transcoding, video tagging, which essentially involves applying machine learning to be able to scan videos on a frame-by-frame basis and make sense of those frames by being able to tag the video, as well as video surveillance and telemetry. These are just a handful of functions that we believe will need to move closer to data and hence closer to storage for us to be able to scale performance in a cost and power effective manner. So I'm going to illustrate a couple of deployment points. The first picture is showing the storage aggregation deployment point, and the second picture is showing the storage endpoint deployment picture. So on the first one, basically what you'll see is that the compute accelerators now need to move into these storage adapters. And by doing so, now you are essentially tackling the first bottleneck. The first bottleneck of the PCI connectivity to the host and the connectivity through the DRAM, system DRAM into the accelerator is now overcome by making the storage adapter adaptive and accelerated. We have multiple partnerships in this space, and I'm going to talk to that later, which will allow customers to now improve performance and essentially get around the performance bottleneck of the connectivity to the host as you move these compute functions closer to storage. The other nice thing about this is that now it becomes more power efficient because now you're moving less data back and forth over to the CPU. In the case of an external storage array, it becomes even more dramatic where you can avoid the back and forth over the network fabric to go to the server rack, and you can do this acceleration within the storage array. On the next picture here, the storage endpoints, it's something that we would have to go to when we get into hundreds of terabytes per server. Here, you want to be able to apply parallelism. By moving the acceleration down into the endpoint, now you can leverage the fact that you have, let's say, 24 or 48 of these drives with built-in acceleration and hence get the parallelism benefit from a performance standpoint. You can now also benefit significantly from a power standpoint because you're processing all that data locally. I'm going to give a simple illustration of this architecture on the next slide. But just to complete this picture, what is also important to recognize is that when we talk about adaptive storage endpoints, we are talking about, let's say, SSDs or NVDIMMs that have FPGA content that can adapt to different compute functions from compression to data dedupe to key value offloads, depending on what are the demands for a given data center at any given instance in time. This architecture will help us go drive performance in a cost and power efficient manner. Another interesting variant that I should talk to, and you will see that in one of the demos in the Xilinx booth, is you can take the SSD form factor like a U.2 form factor, and you can create an accelerator with just, let's say, an FPGA inside it without any media in it. So think about an accelerator that can be plugged in a U.2 form factor, and now it can be a peer. It can be offered as a namespace on NVMe and essentially function as an accelerator that is sitting close to the storage endpoints. The neat thing about that is that you can actually scale this out within a server or within a storage array by replacing many of the U.2s that have media versus balancing it out with having U.2s that have accelerators. So this architecture, we believe, is going to be extremely powerful going forward and will allow us to go tackle the challenge of really large data in our data centers. So let me give you a quick illustration of this solution, and then I'm going to jump into a new area of around how Xilinx is enabling a platform approach to making this happen at greater scale. This is an example of what I would call a typical data mining problem or finding a needle in a haystack problem. Imagine a case where you have a video surveillance system that wants to essentially scan a particular person's image across 100 terabytes of images, maybe videos, that are stored inside these SSDs. The conventional way of moving data to compute would require us to go read all the contents from the SSDs into the CPU, apply a machine learning acceleration technique like CNNs, convolutional neural networks, like a GoogleNet or ResNet or even a YOLO for facial recognition, apply that technique in the CPU/accelerator and use that to essentially decide whether you got a hit or not. But now you're moving 100 terabytes of data from the SSDs into the CPU, into the accelerator. You're burning a lot of power. Most importantly, you're going through pipes that are going to bottleneck from a performance standpoint. The amount of time and effort it's going to take to recognize whether there's a hit or miss for that person's image is going to be substantially larger than what you can do using the new approach. In the new approach, when you move compute to data, effectively what you're doing is you're moving the machine learning accelerator, the convolutional neural network, into the SSD or into a U.2 form factor accelerator. And now you can effectively simply push the image from the CPU down to every single drive in the system and let each drive do the work locally to scan its contents and come back with a match or not. So the amount of data that is transferred is dramatically reduced because all you have done is you have moved an image down from the CPU to the SSDs, and all of the work is done locally, which now is both performance efficient because you're not running into those PCIe bottlenecks, but more importantly, it's going to be extremely power efficient because you're handling it all locally inside the drive. And all of this is happening because you can now leverage the parallelism, and you can do it locally inside the SSD. So that's where we see the data center infrastructure headed in moving compute to data to be able to grapple with large amounts of data going forward. What I would like to now give you is some early proof points of this direction that I talked about, moving compute to data. We have been working very closely with our ecosystem partners who have been innovating in the space. So the good news here is that this is not hypothetical, this is not theoretical, this is real. We have partners on the storage endpoints like ScaleFlux who have used Xilinx FPGAs to deliver both the flash controller logic as well as compression into their architecture. We have other players like Berlewood, Smart IOPS, and Micron who are now innovating in both SSDs and NVDIMM form factors. And we have storage aggregation solutions with the likes of Nalatech and Fidus who have provided cards that can be plugged in as storage adapters that can offload many of these compute functions listed on the left here to be able to deliver that value close to storage. And we have IDTCOM, who is also on display at our booth, who have come up with a clever method of using NVMe standards and NVMe as a transport to run acceleration on top of the NVMe transport. So the list of functions here is, again, a list of functions that we are investing in organically, as well as working with the ecosystem partners out there to enable a broad set of ecosystem players to have solutions available in this space. So the good news here so far is that there are early proof points around this new architectural trend. But the great news here is that we are now investing in this at a much larger level and treating this as a platform investment by developing an ecosystem around it. And I'm going to talk to that next. This is what is going to enable this whole effort to scale. One of the key learnings that we had working closely with Amazon on their F1 instance, which is FPGA as a service, FPGAs that are deployed in the cloud that can accelerate third-party workloads. One of the key learnings was the reason why FPGAs have not been broadly used in the past was because FPGAs were harder to program. There were only so many RTL engineers out there who could do RTL programming and do timing conversions and get the FPGAs to do what needed to be done. What we learned in our engagement with Amazon is the notion of offering a platform to developers. The notion of a platform is the notion of creating a shell and a role and multiple roles. And let me expand on that. The notion of a shell is basically using a technique called partial reconfiguration that's available in Xilinx FPGAs. You can pre-bake all the I/O capability around I/O controllers, PCI controllers, memory controllers, DMA controllers into the FPGA. And now this FPGA card is available to be programmed for different types of roles. The roles can be a database offload engine. The role can be a machine learning, CNN, or a LSTM engine. The role can be a video transcoding engine. So the goal here is to create a platform by offering a shell that is pre-configured, and then by creating these overlay engines. So the overlay engines are engines that run on top of the FPGA hardware. These are pre-compiled and pre-optimized at the RTL level if required. But these now offer a software programming interface to the developers. with an overlay engine called XDNN for machine learning, with an overlay engine for database acceleration like Postgres, with an overlay engine for video transcoding working with a close partner, we are now offering FPGA as a platform to software developers. So the big shift that's happening here is being able to offer FPGA as a platform to software developers and even data scientists. Data scientists are operating not just at C++ level, but they are actually operating at the framework and API level. So we are now offering this platform to data scientists and software developers who can operate within standard frameworks like TensorFlow, like FFmpeg, and they can now develop their algorithms and software and compile in seconds, just like they're used to compiling on CPUs or GPUs. This big shift is really what's enabling an ecosystem of application developers who have never previously used FPGAs, who never understand RTL programming, to now start getting built out. This whole ecosystem that I've shown at the top here is getting built out across life sciences, fintech, machine learning, video. There's a whole ecosystem that's getting built out across multiple types of applications. We intend to leverage all of this ecosystem and in many cases apply this ecosystem to storage endpoint deployments. So to the extent that an acceleration belongs closer to data and closer to storage, we are now going to enable all these platform investment and ecosystem that we are building to be able to bring that ecosystem and platform to the storage. And that's the exciting part going forward. So this is happening with our 16-nanometer silicon. We are going aggressively with this, working closely with multiple partners. But going forward, if you look at the roadmap of innovation that Xilinx has delivered over multiple decades here, from building the first FPGA in the industry to really taking a systems approach to FPGA by innovating around 3D FPGAs, creating SoCs and multiprocessor SoCs, our next step in the evolution of this architecture is what we call as the Adaptive Compute Acceleration Platform. And the key innovation that's going into this platform is around hardening of certain functions onto these FPGA platforms that can help drive more cost efficiency and performance efficiency and power efficiency going forward. One key element is the network on chip. The network on chip on these ACAPs is going to be completely hardened. That allows the FPGA resources to be used for actual kernels or roles, actual applications, versus just connecting the various blocks together. We are going beyond the traditional elements around PCI controllers, memory controllers, DSPs, to now building domain-specific engines that are hardened for specific functions like machine learning. We call them the hardware programmable engines, the hardened programmable engines that can be programmed in both hardware and software. This is the future of adaptable platforms. We are at the forefront of this in terms of enabling these adaptable platforms and bringing them closer to storage to help address some of the storage bottlenecks that we talked about. So with that, I would like to welcome all of you guys to our booth, where we have showcased many of these interesting, innovative solutions in our booth. And I would like to also request all of you to mark your calendars for a big event, Xilinx Developers Forum, that's coming up on October 1st and 2nd, where we'll have some big announcements and kind of reveal some of the details around our platform investments. Thank you.